بسم الله الرحمن الرحيم. سنبدأ إن شاء الله بعرض المحاضرة السادسة من مادة التبريد المخصصة لطلاب الساعات المعتمدة CHP Students Course Number EMM 401. تشمل هذه المحاضرة بعض الأهداف، وهي المقارنة ما بين main components and the auxiliary components of vapor compression cycles, and then we will review the ideal vapor compression refrigeration cycle, and we will show some solved problems. Then we will study the actual vapor compression refrigeration cycle and some solved problems. Then we will evaluate the performance of vapor compression refrigeration with liquid suction heat exchanger and a solved problem based on R744, which is CO2, will be explained in details. Methods of refrigeration. The methods of refrigeration can be classified as a non-cyclic, cyclic, and thermoelectrical. The non-cyclic refrigeration cooling is accomplished by melting ice or by subliming dry ice, which is mean frozen carbon dioxide, which can be used for small-scale refrigeration in laboratories and workshops or portable coolers. Cyclic refrigeration consists of a refrigeration cycle where heat is removed from a low temperature space or source and rejected to high temperature sink with the help of external work using compressors. Cyclic refrigeration can be classified as a vapor compression or gas cycle. Vapor cycle refrigeration can further be classified as vapor compression refrigeration and vapor absorption refrigeration. Types of refrigeration cycles. There are three types of refrigeration cycles. 1. Vapor compression cycle. 1. Simple vapor compression cycle, which have discussed before, and some solved problems based on this simple vapor compression cycle will be discussed during these lectures. Section 1-2 discussed innovative vapor compression cycle. It can be classified into 5 sections. We will discuss through this lecture the first section, which is dedicated for vapor compression with liquid suction heat exchanger. In next lectures, we will discuss the 4 main items: section 1-2 of cascade vapor compression cycle, section 1-3 multi-stage vapor compression cycle with flash intercooler, section 1-4 multi-evaporator vapor compression cycle, even using one compression stage or multi-compression stage, section 1-5 liquefaction of gases, which may be used in industry to liquefy the natural gas and transform it to LNG, then to facilitate its transportation during marines. The second part is number 2, gas refrigeration, which is discussed in lecture number 10, and it's acting like a reversed Brayton cycle. Also, the third part is the vapor absorption cycle, will be discussed also in lecture number 10. And in this system, we will replace the compression using compressor by heat source such as hot water, steam, direct fired using different combustion materials, or exhaust gases of diesel generators. This slide presents the 4 main components of vapor compression refrigeration cycle, which are the evaporator, the compressor, the condenser, and then the expansion device. Inside the evaporator, we find that the low pressure liquid refrigerant in evaporator absorbs heat and changes to gas. Then the compressor increases the pressure of the refrigerant from evaporating pressure to condensation pressure using the work absorbed from the surrounding in a manner of electrical power. The superheated vapor enters the compressor where its pressure is raised. Then the condenser receives these superheated gases to desuperheat it in the first stage of condenser and then complete its condensation until reached to the saturation liquid line as shown on pH diagram and will be discussed in next slides. The high pressure superheated gas is cooled in several stages in the condenser. It may be classified into 3 stages such as desuperheating, condensation, and subcooling at final stage of the condenser. After the refrigerant leaves the condenser, it must be decrease its pressure again to complete its journey inside this refrigeration cycle from state 4 to state 1 when passing across an expansion device such as expansion valve or capillary tube in small size refrigeration machines. Liquid passes through expansion device which reduces its pressure and controls the flow into the evaporator. So the expansion device is responsible to reduce the pressure against the compressor which increases the pressure, and also the expansion device is responsible to control the flow inside this refrigeration cycle. Vapor compression refrigeration key components of mechanical compression chillers. 1. Evaporator. In air coolers, evaporator cools down the return air where the cold refrigerant flow inside the evaporator coil with fans. The refrigerant evaporates and changes it into vapor as the heat is transferred from air to the refrigerant. However, in water chillers, chillers produce chilled water in the evaporator where the cold refrigerant flows over the evaporator tube bundle. The chiller water is then pumped via the chiller water distribution system to the building air handling units. The chilled water as a secondary refrigerant passes through the coils in the air handlers to remove heat from air used to condition space throughout the building. The warm water or returned water transferred from the building ventilation air returns to the evaporator and the cycle starts over. 2. The compressor. Vaporized refrigerant leaves the evaporator and travels to the compressor where it's mechanically compressed and changed into high pressure and high temperature vapor in superheated zone, as will be shown on pH diagram. This temperature may be named the discharge temperature, and it is observed the maximum temperature in this cycle. Upon leaving the compressor, the refrigerant then enters the condenser side of the chiller or the refrigeration machine. 3. Condenser. Inside the air-cooled condenser, the hot refrigerant flows inside the tubes and the cooling air from atmosphere flows over these coils with fans from outside to desuperheating and then condensing the refrigerant to liquid phase inside the condenser before entering the expansion device or valve. However, inside the water-cooled condenser, the hot refrigerant flows around the tubes containing the condenser loop water. The heat transfers to the water, causing the refrigerant to condense into liquid form. The condenser water is pumped from the condenser bundle to the cooling tower, where heat is transferred from the water to the atmosphere. The liquid refrigerant then travels to the expansion valve to reduce its pressure and complete its journey again inside this refrigeration cycle. 4. Expansion valve. The refrigerant flows into the evaporator through the expansion valve or metering device such as capillary tube. This valve controls the rate of cooling. Once through the valve, the refrigerant expands to lower pressure and a much lower temperature to complete its cycle and to enter the evaporator. It flows around the evaporator tubes, absorbing the heat of chilled water that's been returned from the air handlers, completing the refrigeration cycle. This slide presents all the components, consists of the forming components and the special components which may be required to complete the vapor compression function. The forming components listed here from number 1 to number 4, evaporator, compressor, condenser, and expansion valve, have been discussed in previous slides. Now we will discuss the function of the auxiliary components or special components which must be included inside actual vapor compression cycle to complete its work correctly. Its number listed here in this slide, starting from number 5 to number 16. Number 5, oil separator, which is installed on the discharge side of the compressor to separate oil. Then the refrigerant discharged from the compressor and return oil back to the compressor crankcase. Number 6, headmaster, which is connected to balance the mass flow rate going through the condenser in different part load conditions and acting as a bypass device connected in parallel with the condenser pipes. 7. Liquid receiver. The liquid receiver must be connected on the cycle downstream the condenser to collect the liquid of the refrigerant going through outside the condenser and re-suction it in liquid phase to support them to the evaporator before going through expansion device. Filter dryer number 8 may be installed with a side glass number 9 downstream the liquid receiver as shown. Then we can use a liquid suction heat exchange to exchange heat by supercooling the liquid of the refrigerant going outside the condenser by the gas which going out from the evaporator before entering the compressor. This heat exchange may be helpful to increase the COP with some refrigerant. The study must be performed to study the effect on the COP due to the superheating for the evaporator of the gas which going out through the evaporator before enter the compressor, with the subcooling which must be happen to the liquid of the refrigerant going out from the condenser. This effect of liquid suction heat exchange will be discussed and shown on pH diagram in next slides, and also a solved problem will be explain the effect on the liquid suction heat exchanger on the value of the COP in different cycles. Number 12 and number 13, EPR valve and CPR valve, is the evaporator regulation pressure, which regulates the pressure of the evaporator to ensure the performance of the compressor. However, the crankcase pressure regulator valve are also to be connected but near the compressor outside the cycle to control the pressure of the crankcase pressure based on the compressor performance to protect the compressor from falling down or working out its design range and to save its lifetime. Number 14, suction filter. It's recommended to install a suction filter to remove any foreign materials which may be going through the cycle to be enter the compressor with the refrigerants such as dust or any particles of materials during to welding and other like. Number 15, suction accumulator is recommended also to be installed in a suction line to ensure that the amount of liquid of the amount vapor of the refrigerant is sufficient in the suction side of the compressor to ensure the amount of refrigerant to be entered the compressor is correct. Number 16, pressure reducing valve, which is connected on the discharge line on the compressor to ensure that the pressure does not exceed the specified pressure of the condenser and the other system component of this cycle to prevent it from explosion. It should be clear that the liquid line, suction line and discharge line are colored here with different colors. The liquid line, which provides the liquid from the condenser to the evaporator enter, is shown in blue. However, the suction line, which provides the vapor from exit from evaporator to the suction of the compressor, in yellow. And finally, the discharge line, which connects the discharge of the compressor to the enter of the condenser, is shown in red. These colors are actually used in actual cycles to dedicate each line and its function based on these color codes. Yellow for suction line, red for discharge lines, which is the maximum temperature and very hot, and you must not put your hand on this any part of this line. And finally the liquid line, which is dedicated by blue color. This slide shows this slide also. Here we will start to solve. In this slide we can find problem number 2. This is the solution after presentation or pH diagram. Use problem 3 using R717, which is NH3. A simple NH3 vapor compression system has compressor with piston displacement of 2 meter cube per minute, a condenser pressure of 12 bar and evaporator pressure of 2.5 bar. The liquid is subcooled to 20 degrees Celsius by subcooling the liquid line to suction line. The temperature of vapor leaving the compressor is 100 degrees Celsius. Heat rejected to compressor cooling water is 5000 kJ per hour, and volumetric efficiency of the compressor is 0.8. Compute capacity, indicated power, and COP of the system. The white area is dedicated for your solution, and the pressure enthalpy diagram of the used refrigerant ammonia R717 are presented here with the pressure and enthalpy axes. The pressure is shown using bar units and the enthalpy using kilojoule per kilogram. The next slide will present the solution of this problem. The first step, we have estimate the cooling effect using the equation refrigeration effect, total refrigeration effect, which is nomenclatured here as RE equal m dot refrigerant multiplying by H1 minus H4. So firstly we have to go to the chart to present all the cycle corners starting from point 1, 2, 3, 4 to indicate all the enthalpies of the ammonia based on these working pressures, which is highlighted and as inside the clouds shown on the above head of the problem of 12 bar for the condenser pressure and 2.5 bar. These are the two main lines which will contain all the points of the cycle corners based on ammonia pH diagram. Then we can estimate the using the displacement volume Vp equal m dot refrigerant multiplying by the specific volume at state 1 divided by eta volumetric, which have been given. So from this equation we can get the m dot refrigerant, which is equal 3.2 kilogram per minute, where the volumetric efficiency have been given and specific volume, and the displacement volume or piston displacement is given in meter cube per minute of 2 meter cube per minute. So we have get the mass flow rate of the refrigerant in the same unit, kilojoule per minute. If we need to transform it to kilojoule per second, we have to divide it by 60. Then we can get the cooling effect, QCC or Q cooling effect of refrigeration effect, nomenclature here in this solution RE equals 3.2, which is corresponding to the m dot refrigerant multiplying by H1, which have been getting from the chart 1445 minus 300, which is corresponds to H3 and H4. We can get that the RE equals 3664 kilojoule per minute. Then the capacity, we can estimate the capacity of this cycle based on the cooling effect in refrigeration ton, by dividing or the transformation unit from kilojoule per minute per ton, 2 ton refrigeration ton, we have to divide by 210. So we can get the capacity as equal 18 refrigeration ton. Then we will go to estimate the indicated power of the compressor, which named here as a power listed below. Firstly, we have estimate the work of the compressor, of the displacement work performed by the compressor, which is nomenclature in this solution WD, referred to displacement work. It have divided into two parts. Part is dedicated to compression process from H1 to H2 for certain amount of refrigerant. So the first term will be m dot refrigerant multiplying by H2 minus H1 plus the term which have been lost during the cooling of this compressor, as mentioned in the heading of this problem, that the compressor have rejected cooling amount of heat using water, which is equal to 5000 kilojoule per hour, will be used in the same equation, but will be divided by 60 to unify the units of these terminologies or these terms in this equation in kilojoule per minute. Then we can get the work displacement equal to 836, as can be seen by using the figures shown in kilojoule per minute. Then we can estimate the power, the indicated power, by transform the kilojoule per minute to kilojoule per second, which corresponds to kilowatt, by dividing its results 835 divided by 60 to get 13 kilowatt, which is equal to the indicated power consumed by the compressor, and it was responsible to increase the pressure of the refrigerant from H1 to H2 for the certain amount of m dot refrigerant plus the term lost into the cooling water, as mentioned in the heading of this problem. The final part is the coefficient of performance, COP, which equal the cooling effect, the useful part of the cooling effect, RE, divided by the work displacement of this compressor, including the cooling and the term responsible for increasing the pressure of the refrigerant used, which is ammonia. So 3664 divided by 836 will give that the COP equal 4.4. Finally, we have get all the three parts required of this problem using the capacity and the power and the COP. The capacity is 18 refrigeration ton and the power is 13 kilowatt. Therefore, the COP is 4.4, which indicates that the ammonia have high COP relative to another amounts, especially when using water cooling in the condenser, which reduce the condenser pressure to 12 bar rather than other cycles will be presented later on or solved in different kind of problems with higher pressure starting from 18 or 20 or 24 bar. So the effect of using cooling water is highlighted here. Also the effect of subcooling degrees of the inside the condenser at its final stages are increase the amount of cooling effect rather than the increasing of the COP due to the reducing of the condenser pressure when using cooling water, which has effect to reduce the work of the compressor and reduce H2 if compared with air cooling systems. Problem number 4. A refrigeration system using an H3 works on standard vapor compression cycle. The condensing temperature is 30 degrees Celsius. Investigate the performance of the system based on A. COP, B. Mass of refrigerant circulated, C. Volume of refrigerant handled, D. Temperature of refrigerant at the compressor delivery. So it need in item number D the discharge temperature, which is the maximum temperature to be recorded inside this cycle. The system operates at temperature in the evaporator of minus 10 degrees Celsius and 16 degrees Celsius respectively. Capacity of the system is 10 refrigeration ton. Use the properties of saturated NH3, which is ammonia, as listed in the below table shown on this slide. As can be seen, firstly, we have to plot the cycle corners using the two pressure listed or the two corresponding temperature listed of the condenser and evaporator, such as minus 10 degrees Celsius for the evaporator temperature and 16 degrees Celsius for the condenser. Then after plotting, we have get that point 1 has enthalpy 1512.2 1740 in kilojoule per kilogram of ammonia when using ammonia based on the attached pH diagram of R717. And finally we have get from this chart that the H3 equal H4 and equal 340. The first step, the COP, can be estimated regardless to the mass flow rate of refrigerant using a specific change of enthalpy in the evaporator and specific change of enthalpy in the compressor. So the COP equal H1 minus H4 divided by H2 minus H1, we can get that the COP equal 5. Then we can estimate the M dot refrigerant using the cooling effect equation divided by specific cooling effect, which is mean the delta H on the evaporator, so the specific tonnage can be used 210 multiplying by 10, giving 2100 divided by delta H 1 minus H4, which is equal 1172, giving that m dot refrigerant equal 1.8 kilogram per minute or 0.03 kilogram per second if divided by 60. Then the specific volume of state number 1 can be get its value clearly from this pH diagram at state number 1, which have been shown wrongly on this presentation as shown number 2 after the superheating, due to the superheating performed inside the evaporator to increase the load inside the evaporator and to delay the enter of the compressor from the saturation vapor line into the superheated vapor of the ammonia located at this point shown here, which strongly written as a 2. However, it must be state number 1. The correct number 2 is here. The volumetric, then the piston displacement of the compressor can be estimated, assuming that the volumetric efficiency of the compressor is 100%. So the piston displacement normally equal the specific volume at the enter of the compressor multiplying by the m dot refrigerant enters the compressor, giving that 0.48 multiplying by 0.03 equal 0.014 meter cube per second. Finally, from this chart we can get the corresponding discharge temperature, which is the maximum temperature recorded or observed on this cycle on the discharge of the compressor, equal 125 degrees Celsius, as can be seen on this pH diagram attached to the solution. Problem number 5, using R22 vapor compression system includes a liquid vapor heat exchange in the system. A system of a capacity 70 kilowatt operates between -8 degrees Celsius and 42 degrees Celsius respectively. Refrigerant is subcooled by 5 degrees Celsius, shoring the condenser, and superheated by 10 degrees Celsius, shored at the end of the evaporator before entering the compressor. If 4-cylinder single-acting reciprocating compressor with bore-to-stroke ratio 1 to 1.2 and operating at 1200 RPM is used, you are requested to determine A. Ideal COP, which is named Carnot COP, B. COP of this system, C. Mass flow rate of the refrigerant, D. Theoretical piston displacement per minute, E. The bore and the stroke of this compressor. Assuming that the volumetric efficiency of the compressor is 80% and specific heat of the refrigerant equal 1.24 kJ per kilogram Kelvin in liquid phase, and specific heat of the vapor equal 0.74 kJ per kilogram Kelvin. And also the refrigerant properties are given in the below table to use the specific volume and specific enthalpy and specific entropy in different units, such as meter cube per kilogram for specific volume, kilojoule per kilogram for specific enthalpy, and kilojoule per kilogram Kelvin for specific entropy at the main temperatures dedicated in this evaporator and condenser at -8 degrees Celsius and 42 degrees Celsius respectively. The white area is dedicated for your solution, and our solution will be presented in the next slide for this problem in different steps. Firstly, we have to plot the cycle corners as usual on this pH diagram dedicated for R22 by using the cycle coordinates and the two pressure and temperatures -8 and 42, we can locate the two main lines on which all the cycle coordinates will be plotted, taking into consideration the 5-degree subcooled at the outlet of the condenser, which must be taken here, which is located here in point 3, state 3, and also the superheating, which must be taken into consideration during plotting point A away from the vapor saturation line by 10 degrees Celsius of superheating, as we plotted point 3 away from the vapor saturation, the liquid saturation line to the right side by 5 degrees of supercooling, and this 10 degree of superheating to the left side due to the increasing in the temperature at the suction of the compressor, as mentioned in the heading of this problem. Then we will go to estimate the requirements of items A until item E. The first one is the ideal COP, which is equal capital T low divided by capital T high minus T low from kernel theory equal -8 plus 273 divided by 42 minus -8, which is correspond to 42 plus 8, giving COP is equal 5.3. Then we will go to item B to estimate the COP of this system as shown. COP equal H1 minus H4 divided by H2 minus H1 from the enthalpies we have get from the pH diagram of R22. We can get that H1 equal 410, H2 equal 449, H3 equal H4 equal 244. So the COP of this system will equal 4.25, which is lower than the kernel COP, which is listed in the above line, equal 5.3. Then will we go to estimate the mass flow rate of the refrigerant, and item C, m dot refrigerant will equal the cooling effect, the total cooling load in kilowatt divided by the cooling effect, the specific cooling effect inside the evaporator, which is equal H1 minus H4. So m dot refrigerant equal 70 kilowatt divided by 410 minus 244, which is gives that m dot refrigerant equal 0.42 kilogram per second. Item number D, theoretical piston displacement per minute in meter cube per minute, using the equation of piston displacement, which have been discussed through many problems previously. Piston displacement equal m dot refrigerant multiplying by specific volume of state 1 at entering the compressor divided by the volumetric efficiency, which is given in this problem 80%. So the volumetric displacement or the volume flow rate in meter cube per second will be equal 0.42 multiplying by 0.06 the specific volume divided by 0.8 the volumetric efficiency, gives that the displacement volume equal 0.325 meter cube per second. By multiplying it by 60 to transform it from meter cube per second to meter cube per minute, we can get that the displacement volume or piston displacement is equal to meter cube per minute. Then item number E, which is need to estimate the bore and the stroke, the diameter of each cylinder and the stroke of this compressor from top dead center to bottom dead center of each cylinder. The displacement volume can be estimated by the volume of each cylinder multiplying by the number of cylinder multiplying by the RPM. So the equation volume displacement equal pi over 4 multiplying by d square, which corresponds to the area of the cylinder, multiplying by L, which indicates to the stroke of the cylinder, multiplying by capital N, which indicates the speed in RPM, and K, the number of the cylinder, which is given in this problem 4-cylinder compressor complete with 4 cylinders. The second line, the line after that, we can using the equation, the same equation, but putting the displacement volume in 2 meter cube per minute in left hand side, and we just have two unknowns, which is diameter or the bore of the cylinder and the stroke, and there are a certain ratio given in this problem between the bore and stroke is equal 1 to 1.2, so we can replace the stroke with 1.2 the diameter, and using the 1200 RPM and 4 number of cylinder, so the equation will just have one unknown to be solved, which is the diameter cube. We can get, after solving this equation, we can get that the bore of this cylinder is equal 76 millimeter after transforming it from meter cube, and then we can estimate the stroke in basis of the diameter of the bore by multiplying 1.2 by 76 millimeter to get that the stroke of this problem or this cylinder used inside this compressor is equal to 98 millimeters. After we have solving 5 problems based on the simple vapor compression cycle, we could see some problems which may be including liquid suction heat exchange by superheated the vapor going out from the evaporator before entering the compressor, and the heat to be gained to this vapor is transferred from the subcooled at high temperature at the outlet of the condenser. By this heat exchange, it may be increase the COP for certain number of refrigerants, not all the refrigerants. We can use this heat exchange between liquid line and suction line. Also, it has a limitation, and the comparison must be performed before estimate the degree of superheated, the number of temperature rising before entering the compressor, and also the number of temperature limits in subcooling at the end of the condenser. It should be clear that the subcooling will increase this amount here, and then 0.4 and 0.3 will be switched to the right hand side, which will increase the cooling effect due to this subcooling which happen in the outlet of the condenser, and this amount of heat on pH diagram will increase the COP in its upper part. However, the superheated here will maybe increase the work required by the compressor due to the diversion of the constant S lines in this direction. So the projection area from point 2 dash minus 1 dash is larger than the projected area from point 2 to point 1. So the work of the compressor will increase slightly due to this superheated, which is a must when we perform this subcooling between the two suction line here and liquid line here. The amount of heat must be balanced when using this liquid suction heat exchange, and the effect on the COP must be studied carefully before take into account this superheat and subcooling during the design issue of the refrigeration cycle. This slide finally concludes the effect of the subcooling and superheat if compared between point 1, which we put it on the saturation vapor line all of the time, and point 3, which put it on the liquid saturation line all of the time. When switched this point 3 as shown here to the right, we gain the cooling effect by this amount, and when switching this point 1 to the right direction, we will lost and we have to pay a larger amount in a work of compressor. Then we have to compromise the gain from the subcooling due to the cooling effect increasing by this delta H, and the delta H increasing in the compressor, and take the decision if we need the superheat and subcooling liquid suction heat exchange to be attached, or the system must be equipped with this liquid suction heat exchanger or not, and also the amount of superheating degree and subcooling degree to be considered according to the number of refrigerant or the type of the refrigerant to be used in the system under design. This slide also complete showing the effect of the liquid suction heat exchange and its presentation on pH diagram by switching or moving the saturation vapor line at entering the compressor by certain degree of superheating and to the right direction on pH diagram, and also the effect of increasing of cooling effect by switching this point D from at the exit of the condenser, and delay the exit of the condenser maybe happen inside the condenser by condenser itself, or maybe this subcooling will be happen outside the condenser inside the liquid suction heat exchanger as shown before, and will show also in the next slide after this slide directly. Here we can see again the four main components of the cycle, of the vapor compression cycle, and complete with the special system components which the system may be equipped with to ensure the function of the vapor compression cycle. Especially we will highlight here in this slide on the liquid suction heat exchange, which is located just upstream to the evaporator heat between the liquid line before entering the expansion valve and the suction line after going out from the evaporator. This liquid suction heat exchange may be constructed by tube-in-tube heat exchanger or shell-and-tube, small shell-and-tube heat exchanger, or may be constructed by soldered between this portion of liquid line before expansion device and the suction line just after the evaporator outlet connection, as can be seen on this moving cycle inside the four main components and the special components the system equipped with as shown in these figures. Also pH diagram are still here to present the effect of superheating and subcooling between the suction line before entering the compressor after going throughout the evaporator, and the liquid line just before entering the evaporator and entering also the expansion device at high pressure and high temperature, so that will allow the heat to be exchanged or transferred from the condensation temperature after this subcooling temperature to the lower temperature. However, it's in vapor phase, but at lower temperature, which corresponds to the evaporating temperature, and some temperature will be rise in superheating of the suction line to reduce the temperature of the condensation temperature by certain degree of subcooling, as shown on the attached pH diagram, and as can be viewed inside the heat exchanger this system is equipped with, and many problems have showing that during solving previous problems in this lecture, and also the major problem of the suction liquid heat exchange for CO2, which we'll discuss in the next some slides. The residual slides in this lecture is dedicated to solve a problem of CO2, which is R744, using liquid suction heat exchange, as can be seen in the attached line diagram. The problem heading is as following. Use the R744 refrigerant property table in order to evaluate the following. Determine the work done on the compressor. B. Determine the heat rejected to the hot water heater and that rejected to the space heater. C. Determine the coefficient of performance of the hot water heater and the space heater. Recall that the COP is defined as the desired heat transfer divided by the work done on the compressor. Item D. Determine the coefficient of performance of the air conditioner. Notice that on the pH diagram that the internal heat exchange significantly increases the capacity of the air conditioner. The line diagram shown in this slide, showing the compressor here in this side, to increase the pressure of state 1 to state 2. The state 1 pressure is equal to state 6, which is 3.5 megapascal. Such the internal heat exchange is adiabatic from the internal outside and also does not affect the pressure. So the pressure of state 1 is equal to state 2, and also the pressure of state 3 is equal to state 4 and equal to state 2 at this high pressure side. The compressor compresses the refrigerant R744, which is CO2, from state 1 and temperature at pressure P1 3.5 megapascal and T1 30 degrees Celsius adiabatically in adiabatic compression process to state 2 to gain pressure P2 13 megapascal and T2 160 degrees Celsius. Then the superheated refrigerant is go through this hot water tank to be cooled, the gas to be cooled, and the hot water will gain the heat at constant pressure process heat removal from the gas, which is the CO2, and the hot water will gain this amount of heat, which is reduce the gas temperature from T2 160 degrees Celsius to 70 degrees Celsius, which indicates here number T3A, and pressure 3A, which is still constant during the second stage of heat removal in a space heater that will cool down also the CO2 and add heat to this space. So this cycle can be acting as a heat pump. So the heat exchange, liquid suction heat exchange may be useful with some certain of refrigerant during heat pump processes, even for hot water or for hot air conditioning system. Then the temperature T3A is reduced of the gas from 70 degree to 45 degrees Celsius. We will note after this slide that the gas is above the critical point, so the temperature is pronounced here to be reduced from 160 to 70 to 45 degrees Celsius in the gas cooling system rather than the condensation. There is no condensation process, but it is heat removal process, and these gas cooler sections in different sections we can use this gas cooling to increase the hot water temperature and also to condition a certain space. That is main concern for using CO2 in some heat pump system, acting as a heat addition system to water or to space. Then after point 3, stage 3, we will go to this internal heat exchanger between the suction line of the compressor to reduce the temperature of point 3 from 45 by certain degree of subcooling or without subcooling by decreasing its temperature by gas cooling, not subcooling, due to there is no condensation process, as will be shown on the next slide when presenting this line diagram on the pH diagram dedicated for CO2. After state 4, we will throttle adiabatically constant H process and adiabatically without heat removal or addition to state number 5, and then we will go to through evaporator using constant pressure process such P5 equal P6 equal P1, such as mentioned that the heat exchanger, liquid suction heat exchanger, doesn't exchange or slightly exchange the pressure, which is neglected if compared within the lower pressure limit of the cycle of this side, starting from here lower side until this is lower side pressure, and the higher side pressure which is located here from the discharge of the compressor due to gas cooler section and then the liquid suction heat exchanger until reached to this throttle device, which may be used as an expansion device. We will go now to the next slide to continue this problem. As can be seen here, we have made the heat balance equation between these two sides of liquid suction heat exchange. The heat added to the suction line increasing the temperature of 0.6 to 0.1 to reduce the temperature of the gas to be cooled from T3 to T4. So the gas comes here to enter this shell around this tube of suction line with blue. However, the gas to be cooled entered at state 3 around this tube to be cooled, reduce its heat temperature, and going to continue its journey to the rest of the cycle at state 4. However, the suction, which is outlet the suction line to be entered the compressor and which have came from the evaporator, have been gain heat from this gas to be cooled at high temperature. So Q61 equal H1 minus H6, such H1 is higher than H6, and Q removed from the gas side equal Q34 equal H4 minus H3. The equality must be happen with respective to the sign convention of the thermodynamic processes, and taking also into consideration that H4 will equal H3 minus H1 minus H6. That can gives us the equality and the status, the all states of 0.1 and 0.6 and 0.3 and 0.4 during this heat balance equation will be performed additional to the heat balance to be performed on hot water tank and space heater as a gas cooler sections, and also to estimate the Q in the evaporator using the same equation for air conditioning purposes as required in this problem heading. Here in this slide we recall the pH diagram for carbon dioxide refrigerant with number R744 in two axes, pressure in megapascal and enthalpy in kilojoule per kilogram. The saturation line is shown in black and the isotemperature line is shown in blue, and the volume, specific volume, ISO lines is shown in purple, and the constant entropy line, ISO S line, is shown in light blue. In this slide, we have plotted all the cycle corners dedicated for the shown line diagrams, which is shown on the left hand side in this slide, and its presentation on pH diagram of CO2 is shown in this right hand side on this slide. It should be clear the superheating performed between 0.6 to 0.1 inside this liquid suction heat exchanger to be superheated by cooling the subcooled or the gas to be cooled from state 3 to state 4 by this delta H shown on this pH diagram before entering the throttle device and going through the evaporator and superheated by certain degree of superheated can be estimated from here, from this temperature line to this temperature ISO line. We can get this temperature line equal to 30 degree as mentioned here, T1 equals 30 degree, and the evaporating temperature is 3.5. We're using the line of 3.5 megapascal to get these points. Then we can estimate this temperature line, which is 0 degrees. So the superheating is equal about 30 degrees Celsius from 0 to 30, from 0.6 to 0.1. However, then we will go with adiabatic compression to 0.2, which is dedicated here by temperature and pressure. So the isentropic efficiency have a certain value less than 100%, and this line must not be parallel to the ISO efficiency line, and we will locate 0.2, 0.3a, 0.3 and 0.4 on the shown pressure 13 megapascal of P2, P3, P4 are equally at line of 13 megapascal, which is located here, which is equal around 130 bar. Very large amount, so we should take into consideration that this line is, there is no condensation happens here due to this pressure is very high and higher than the critical point, which is intersection point between the vapor saturation line and vapor liquid line. So the gas to be cooled from 0.2 to 0.3a to lost heat to the hot water tank as shown here, Q hot. Then the second part is to the are dedicated to space heating for to reduce the gas temperature from T3a, which is around 72 degrees Celsius as shown from this ISO temperature line. This temperature was around 161 or 160 degrees Celsius as shown on this ISO temperature lines, which is values are shown here on these blue lines. Then the temperature will be reduced in third part using the liquid suction heat exchanger, the main issue of this problem, by the heat to be superheated or to be gained to the superheated steam in the suction line to reduce its temperature from T3 to T4. T3 is around 45 degrees Celsius, such a slide between 40 degrees Celsius and 50 degree, and then number 4 is on the line of 30 degrees Celsius. The heat exchange limits corresponds here to the theory of heat transfer inside heat exchangers. You can review it by yourself. Then from point 4 to point 5 we have to expand to reduce the pressure from 13 megapascal until reach 3.5 megapascal, and you can get now all the cycle corners and its values of H1 equal around 480, H6 equal around 440. You have to check these values carefully. H2 is equal 570, H3A is around 400 in kilojoule per kilogram, or these values of enthalpies. H3 is equal around 310, H4 and H5 are equal around 270. You can put all these values to make the heat balance on liquid suction heat exchanger to get the work of the compressor, to get the heat added to the hot water here, from which have the gas cooled with certain amount of temperature in gas phase, starting with gas and end with gas, and then going to gas cool second stage to air condition by heat addition. In winter cycle air conditioning system, we can use this amount of heat starting from here to here, 0.3823, and finally the necessary liquid suction heat exchange, which may increase the delta H of the enthalpy here, which will be gain in the air conditioning load, which are requested in the final item of this problem. In the next slide we will show an enlarged pH diagram for this solving problem. As can be seen here, this is a pH diagram which I have discussed in the previous slides, and finally we have get all the corners of the cycles and shown all the points, and we can estimate all the enthalpies according to the two pressure limits which this cycle are working based, taking into consideration the heat balance equation performed on the liquid suction heat exchanger in this problem, and also the work of compressor, which is listed as adiabatic compression, not isentropic, so it's not equal, not parallel to the liquid to the iso efficiency line. We will take this into our calculations consideration, and then the heat amount here and the heat amount here, and the heat finally the heat to be removed from certain space for cooling. Thanks for watching, and we will continue next lectures about the lecture number 7 will be dedicated for the different types of refrigerant and the usage of each type and the classification of the whole numbering system for this refrigerant site. Later on, lecture 8 and lecture 9. Lecture 8 will be dedicated for the residual innovative refrigeration cycle, which have been discussed in the start of this slide shows. Then in lecture 9 we will go through most common problem on this innovative vapor compression cycle. In lecture 10 we will go through the gas refrigeration and the vapor absorption cycle. Thanks for watching, and we will seeing you in the next lecture, inshallah.